The time value of money is a major component of our everyday lives. Today, I will talk about present values and perpetuities, and how the formulas associated with each of these can help you make better financial decisions. Let's begin with a simple building block, the present value formula. A present value is the value of some future amount of money in today's terms. Now let's define some values. I'm going to use A for amount, I for interest rate, and N for the number of periods of time into the future. So our present value will be calculated as A divided by 1 plus I to the N. One way to think about the present value is to think about it as how much cash you would need to invest today in order to have a specific future amount. Many things in your life are present values, such as the principal balance on your student loans, on any credit cards you may have, or on your mortgage. The first cash flow instrument I'll look at is a perpetuity, because they serve as a foundation for other types of cash flows. A perpetuity is a fixed payment that will occur over and over forever. Imagine that you are paid $A every month forever and ever. What is the present value of that given an interest rate? Well, if we construct the series of present values, then it appears to be a never-ending sum. However, this formula simplifies down to a very important and simple formula. A divided by I, subject to I being greater than 0. This key mathematical expression will be used in many other financial expressions. Next up is an annuity. An annuity is a series of fixed payments made over a finite timeline. In another sense, an annuity is a perpetuity with an end date. If we write out our perpetuity present value formula, we can convert it to an annuity by cutting it off at some end point. How can we calculate the present value of this annuity? Well, let's look at it as two perpetuities, one that starts today and one that starts at time n. If we subtract these perpetuities from each other, we end up with our annuity present value equation. And if we look at our perpetuity starting from time n, we can also see that it is the same as the perpetuity from time 0, except all of our terms have been divided by 1 plus I to the n. We have a shorthand equation for a perpetuity, and so with it we can calculate the present value of an annuity by subtracting these two present values from each other. This formula then simplifies down somewhat to A times 1 minus 1 divided by 1 plus I to the n divided by I. The factor derived to the right of the A is occasionally called the amortization factor. So with these key terms and formulas out of the way, why would we use these? Well, these formulas are the underpinnings for calculating the payments for loans under different scenarios, and you could use them to evaluate the impacts of refinancing or consolidating multiple debts together. Let's look at an example problem recently posted to our Excel. Suppose I have a 25-year mortgage for $1 million that has an interest-free period for the first 4 years, and the remaining loan term accrues interest at a 4.9% rate. What would the fixed monthly payment be for this loan? And then, how do these loan terms compare to other loans, such as a standard fixed-rate interest loan? To solve this, we know that the present value of our mortgage payments will equal the principal value of the loan. Further, we know that the loan is equivalent to two annuities, one with 0 interest for 4 years starting today, and then one with 4.9% interest for 21 years starting 4 years from now. One special scenario for this: when interest rates are 0, then the present value is simply the accumulation of all of the payments. So annuity 1's present value will be 48 times the payment A. For annuity 2, the present value will be 252 months of payments, discounted for the initial 4 years of 0 interest. When we add these two annuity formulas together, we have a formula that we can solve for the monthly payment necessary for this combined loan. When we solve for A, we'll determine that the fixed monthly payment for these loan terms would be $4,838.56. That's somewhat helpful, but what if we're shopping across different loans? What interest rate would a fixed-rate loan need to be in order to compare against this offer? Well, let's plug our calculated payment into another loan model, one with a single interest rate and 300 months of payments. Here, we can solve for I to determine the break-even interest rate. However, you're going to want to use Excel and GoalSeek or a specialized financial calculator in order to do this. So using some algebra to move terms around, we can identify that our target amortization factor is 206.673. When we plug this into Excel and use GoalSeek, we can discover that the break-even interest rate is 3.23%. That means that any loan with a 25-year fixed rate under 3.23% would be a lower total cost to pay off than our 4 years of no interest with 4.9% interest thereafter. These basic formulas form the foundation of many common financial functions, create comparisons between different loan terms such as adjustable rate loan options, interest-free periods, and fixed loan rates, compare and contrast cash flow valuations between different investment instruments, including common annuities or life insurance policies, make smart investment and repayment strategies to take advantage of different special loan terms, such as determining specialized payment plans to target key payoff dates. All of this with just a few simple formulas mixed and matched together algebraically.